Hi everybody, this is Mr. Slomka, and this is going to be video 2 of 2 on section 8.5, which is recursive formulas. So now this is the exciting example. This is the one that I've been building up to. This is going to be on the very top of the back page for your recursive notes. And so this example right here is going to really drive home the reason why recursives exist and why we didn't learn about them right away, why we saved them until later. So what we have right here is we have a very simple little sequence. -3, 12, 27. And the first thing that I wanted to do is I wanted to analyze it and I wanted to understand if it was arithmetic or geometric. If you perform a little subtraction on these, you'll find out you get the same answer of 15 each time, which means this one isn't arithmetic. Now what I have is I have a couple of questions that are similar to each other but slightly different. And that similarity is important and that difference is critical. So let's see if we can take a look. For the first question right here, it says write a rule, and for the second question right here, it says write a rule as well. Now the difference is going to come from the back part right here. For your first question, it says write a rule and use it to write the first 8 terms of the sequence. So now, here's the deal. If you are trying to write 8 terms, that means you're going to have the first and then the second and the third and the fourth and the fifth and the sixth and the seventh and the eighth. The fancy term for that is they're going to be consecutive terms. Because they're consecutive terms, the recursive formula is going to be great because the recursive formula only relies on knowing the previous term. So if you want the second term, you need to know the first. And if you want the third term, you need to know what the second was. All of that information is important to the question, and all of that information is easy to find. Here's our recursive rule, and the way that I would use it is very similar to what I had done before. You can copy some of these first couple answers down, which is great, but I can also do the same type of thing that I had done in my calculator. I know that my first term is -3, and I also know that my common difference was 15. So if I just simply hit the plus sign and the 15, my calculator will start spitting out all of the terms in the recursive. It's thinking about the problem in a recursive way, and it's giving me the answers to my recursive very quickly and very conveniently. Even if I wasn't using my calculator, I could use my brain and get these answers very quickly and easily because they're not that difficult. It's just simply adding 15 each time, and it goes pretty smoothly. So that's great. There you go. No harm, easily taken care of. Now let's talk about the second question. The second question is asking us to write a rule, and it says use it to find the 80th term in the sequence. So a couple of things to note here. Right off the bat, some people might say, well, why don't I just use the rule that I already have? And that sounds like a great idea. There's no sense in reinventing the wheel if you've already got a good rule going. The problem with that, though, is that the 80th term is the thing that we're after. In order to know what the 80th term is, you would need to know what the 79th term is, and you would need to plug it in. But I don't know what that is. And so in order to get that, I'd have to know what the 78th term is, but I don't know what that is. And so I'd have to go down to the 77th, and the 76th, and the 75th, and the 74th, and the 73rd. Basically, what you'd be doing is you'd be making a list of terms that was 80 terms long. I didn't have a problem when I had to make a list of terms that was 8 terms long, but if you're going to make me make a list that is 80 terms long, now I've got a problem. I don't want to do that. It's a waste of my time. So this is when the recursive formula stops being so great. And then when the recursive formula is not great, that means it's time to reach back for the explicit formula. Good old faithful explicit formula. The explicit formula will work a lot better because it only requires you to know a term's location. It doesn't require you to know the previous term. So our explicit formula for this problem is going to rely on the same two numbers, -3 and 15. But the way you work with them is different, and that is the key thing. If I am interested in the 80th term, all I need to do is plug in the number 80, and I can calculate very quickly and easily what that 80th term is going to be. That was not difficult. But asking me to make a list that was 80 terms long, even to do it with my calculator, doesn't sound like much fun. So this is definitely a case where the recursive works sometimes and the explicit works sometimes. So let's get that nailed down. How about this? Take a couple seconds and see if you can answer question C right here. Pause the video, and then I'll share my answer with you. Here's my answer for question C. It says, when is it best to use the recursive formula, and when is it best to use the explicit formula? Recursive is best for lists of consecutive terms. So if they ever mention that they want the first 5 terms, or the first 12 terms, or the first 12 rows in the movie theater, or the first 80 people to cross the finish line at the race, that is when a recursive is going to be best. An explicit is going to be best if you're interested in an individual term, specifically if that term is way out there in the middle of nowhere, like the 80th term, or the 100th term, or the 1,252nd term. Something like that is going to be where the explicit formula is going to be best. Because the explicit formula works on a term-by-term basis, you can also use it in this case over here. It just is a little slow. The recursive is very much a shortcut. It's not maybe the best way to do it, but it is a really, really efficient way to do it. So it's always good to have this in your back pocket. But if I was only going to let you pick one of these to have for forever, I'd want you to have this one. All right, last question right here is our story problem. I like story problems, and this one's a good one. It's also going to point out something interesting. So the story right here says, once upon a time, there was a great explorer who was named Erich Wolfgang V, and he had discovered a lake, and he called it Lake Thompson. The lake initially contained 5,000 fish. After discovering the lake, people came from all over the world to fish at Lake Thompson. At the end of each year, the fish population would be reduced down to 80% of what it had started at. Now, Erich Wolfgang would panic at this point, and what he would do is he would increase the fish population by adding 500 new fish to the lake. That all sounds very good. Good conservationism. Nice job, Erich Wolfgang. Everybody gets to enjoy the lake, but the fish population is going to get replenished. Let's take a look at what's really happening here. So now on the front page, what I wanted you to note is that we had terms like A0, and we also used A1, and this is why both exist. Right here it says how many fish were in the lake when Erich Wolfgang discovered it. So now please remember that at this point, no one has gone fishing there at all. There has been 0 fishing, which means that this is term A0. Now, A1 means that 1 full year of fishing has occurred, and that means 2 basic things have happened. The first thing is people have pulled fish out, which means that our 5,000 fish has been reduced to 80% of what it once was. We're going to take our 5,000 and multiply it by 0.8. This will shrink the amount of fish. But then, the other thing that's going to happen is that Erich Wolfgang is going to notice that the fish population goes down and add 500 new fish. When both of these things happen, the fish population is now 4,500 fish. So I noticed that after the first year there are less fish, but it doesn't seem too bad. If we could just maintain this number now, that would be pretty good. But let's move on to year number 2. The pattern is very much the same. Our fish population is going to decrease because people are going to be pulling the fish out. And then Erich has a panic attack, and he adds the 500 new fish to the situation. And now our fish population is down to 4,100 fish. This isn't looking good for Lake Thompson. I'm starting to feel worried. Next one. More people show up, and more fishing happens, and more delicious fish dinners. Erich Wolfgang goes through his usual conservationist ways and adds on the 500 new fish. And now we are down to 3,780 fish. The fish population is incrementally decreasing as we move from one year to the next. So now the next big question is, can you write a recursive formula for this? So now on the front side, we had been given 2 recursive formulas that we could possibly use. But the big question is this pattern that we're using, are these answers that we're getting, are they arithmetic or are they geometric? And the answer to that is both and neither. This portion of the pattern where we multiply by 0.8 each time is very geometric. And this portion of the pattern where we add 500 each time is very arithmetic. So our pattern shows both. But as you move from one number to the next, there is no common ratio and there is no common difference. So it can be both and neither at the same time. Now, typically in this situation, what happens is that we cannot write a rule then. We get jammed and we can't do anything. But because this is a recursive, and because we can clearly see the pattern that is occurring, you can actually write a rule this time. I know that in year 0, there was 5,000 fish, so there's my gimme. And I also know exactly what happens each year. Each year, the fish population that we had from last year is reduced by multiplying by 0.8. But then, also, each year, the fish population is boosted slightly by adding on an additional 500 fish. So we can actually write a rule. This rule is not arithmetic or geometric, but rather both. This portion is the arithmetic part, this portion is the geometric part. Okay, try out the 8.5 worksheet, and please leave me a question or talk to me on Zoom if there is any confusion or misunderstandings. Thank you so much. This is video 2 of 2 on section 8.5.